In our last lecture, we left off with an example that the single neuron could not handle. We were detecting whether Rob was bluffing at poker, and there was a trend where the more red his face was and the more frowny he was, the more likely he was telling the truth. Except when we got to extreme degrees of redness and extreme degrees of frowniness, then all of a sudden he was bluffing. And this broke the trend. So it turns out that single neurons are not able to handle what are called non-linearly separable problems. Linearly separable problems are problems where the patterns in the data follow a single monatomic trend so that they can be separated linearly. In one dimension, this means there's a single point that separates the different types of data. In two dimensions, this means there's a line that can separate your different types of data. And this generalizes to more dimensions. The limitation to linearly separable problems is a problem because typically the patterns that we need to detect in the real world are much more complicated than this. What we really need is a model that's flexible enough to find any sort of mapping between inputs and outputs. It turns out we can do this with multi-neuron networks. In this lecture, I'm going to give the intuition for why expanding to beyond more than one neuron can allow us to solve the non-linearly separable problems that a single neuron cannot. We'll do this by looking at the binary logic problem known as the XOR problem. So what is XOR? XOR is a binary operator, and binary operators are conditional statements that impose requirements on two individual true-false statements to produce a third true-false statement. You might be more familiar with XOR's counterparts, which are the binary operators AND and OR. AND and OR are also binary operators like XOR, but they are also used as common words that we use in everyday communication. Let's show this with some examples. Say you're attending a party where the host is quite demanding and asks everyone to bring both a drink and an appetizer. The host has specified something using an AND binary operator. The binary operator AND functions like the word AND in everyday language. Both conditions on either side of the AND operator must be true in order for the operator's requirements to be satisfied. So if you brought a drink and an appetizer, the AND condition is satisfied. If you brought a drink and no appetizer, the AND condition is not satisfied. If you brought no drink and an appetizer, the AND condition is not satisfied. And if you brought no drink and no appetizer, then the AND condition is also not satisfied. I want to clarify that these statements that the binary operators act on can be defined either in the positive or negative sense. And then the operator's requirements are evaluated based on however you defined your statements. So if you defined a statement using a negative condition, such as not something, the binary operator will evaluate its requirements relative to the negative condition that you specified. So for example, imagine a host has already carefully planned their menu and does not want any extra dishes clashing with their perfectly conceived menu. In this case, they might require their guests to bring only drinks and not an appetizer. The host would use the AND to impose drink and no appetizer. In this case, if you brought a drink and an appetizer, you would violate the no appetizer condition, and this AND condition is not satisfied. If you brought a drink and no appetizer, then you've satisfied both conditions on either side of the and this condition is satisfied. If you brought no drink and an appetizer, you violated both conditions on both sides of the and the condition is not satisfied. If you brought no drink and no appetizer, you've only satisfied the no appetizer condition, but you did not bring a drink, so the condition is not satisfied. Now let's discuss the OR. Imagine you have a more laid-back host and they say, bring a drink or an appetizer. So with the binary operator of OR, for the specification drink or appetizer, what we have is if you brought a drink and an appetizer, that's okay, because this OR is a lenient OR, and the condition is satisfied. If you brought a drink but no appetizer, that's fine, because you could bring a drink or an appetizer, so the condition is satisfied. If you brought no drink and you brought an appetizer, that's okay, because you were to bring a drink or an appetizer, so the condition is satisfied. But if you brought no drink and no appetizer, then you didn't bring a drink or appetizer, so the condition is not satisfied. I want to point out here that the logical operator OR is lenient in the sense that if you bring both a drink and an appetizer, you will have satisfied the requirements of the OR. This is different than how we might use OR in common language, because there are many times in common language usage when we use the word OR, we'd mean an exclusive OR, such as in, he was either on the 4 o'clock train or the 5 o'clock train. Here, I don't mean he could have been on both trains. I meant he was either on the 4 o'clock or the 5 o'clock. However, the binary operator of the logical OR is lenient, in that it means that if both statements are satisfied, then this satisfies the condition. Now let's talk about XOR. Imagine you have a very conscientious host that doesn't want anyone to feel that they brought more than anyone else, and so this host wants you to bring either a drink or an appetizer, but not both. So now this host is presenting an XOR requirement. They've said to bring a drink, XOR, appetizer. So what this means is if you bring a drink and an appetizer, you've violated their condition because they said to bring a drink, XOR, appetizer, which means not both. So the condition is not satisfied. If you bring a drink but no appetizer, then it's okay. That satisfies their condition. If you bring no drink and an appetizer, again, that's fine. You've satisfied their condition. If you bring no drink and no appetizer, you've not brought a drink, XOR, appetizer, and the condition is not satisfied. I want to show how a single perceptron model cannot handle XOR, but how a multi-perceptron model can.